Hello, good afternoon everyone. This is Dr. Abdul Pasha, Assistant Professor, Department of Electrical and Electronics Engineering, Institute of Aeronautical Engineering, Dundigal, Hyderabad. So this is about all regarding the course of Power System Operation and Control. Here in this case, today's topic is modes of TCS operation. Here in this we will discuss about various control modules, thyristor controlled switched operations that we will discuss now. Modes of TCS operation. So these are bypassed thyristor mode, blocked thyristor mode, partially conducting thyristor, or we may treat it as vernier mode. The first case is bypassed thyristor mode. In this bypassed thyristor mode, thyristors are made to fully conduct with a conduction angle of 180 degrees. This is the angle called conduction angle, that is about 180 degrees. 180 degrees is the conduction angle for bypassed thyristor mode. So gate pulses are applied as soon as voltage across thyristor reaches zero value, and it becomes positive, which may result in continuous sinusoidal flow of current through the thyristor valves. So here TCSC module will act like a parallel capacitor inductor combination. Parallel capacitor inductor combination. Like this it will may exist. This is about TCSC, parallel capacitor and inductor combination is existing. However, here the net current through the module is inductive in nature. So for the susceptance of the reactor, it is selected to be greater than that of the capacitor case. So this is also known as thyristor switched reactor. The other name is TCSC is TSR, thyristor switched reactor mode. So bypassed thyristor mode is different from the bypassed breaker mode. Bypassed thyristor mode is here, bypassed breaker mode. This is existing in the circuit. So here in which circuit breaker provides across the series capacitor, which is close to remove the capacitor, or TCSC module in the event of TCSC faults, or which may be transient over voltage across the TCSC connection. So this mode is employed for control purposes and also for initiating certain protective functions. So whenever a TCS module is bypassed, means from the violation of the current limit, finite time delay is considered. That is T delay. This is represented with the TD, finite time delay, which must be elapsed before the module, and it can be reinserted after the line current falls below the specified limit. So this is the circuit made where this capacitor arrangement is connected in parallel with the inductor case here, and anti-parallel combination of two thyristors are designed here. T1, T2 are the two thyristors. They are connected in anti-parallel manner. Coming to blocked thyristor mode. What happens in this mode means this is also known as waiting mode. So firing pulses to the thyristor valves which are blocked. If the thyristors are conducting and blocking commands are given, then thyristor turns off immediately as the current through them reaches to zero crossing value. So as to make the TCSC module, so it is reduced to a fixed series capacitor combination, and the net TCSC reactance is capacitive in nature. So what happens in this mode means DC offset voltages of the capacitors are going to be monitored and they quickly discharged using a DC offset control. So without that causing any harm to the transmission system of the transformers. So the arrangement made as parallel connection of C and L with anti-parallel connection of two thyristors T1 and T2 makes the circuit to be effective. Next case is partially conducting thyristor, or it may be treated under Vernier mode of operation. So this mode allows the TCSC to behave either as a continuously controllable capacitive reactance, or it may be a continuously controllable inductive reactance. So this may be XC case or it may be XL case, inductive reactance case. So here it is supposed to be achieved by varying the thyristor fire angle in an appropriate range. So however, smooth transition from capacitive to inductive mode is not permitted. This is because resonant region between the two modes are existing. So a variant of this mode is the capacitive Vernier control mode. So what happens in this means thyristors are fired when the capacitor voltage and the capacitor currents have opposite polarity. So this condition causes the TCR current that has a direction opposite to the capacitor current, and thereby which may result in loop current flow in the TCSC controller case. So loop current increases the voltage across the FC, which effectively enhances the equivalent capacitance reactance and series compensation levels for the same value of line current case. So to pre-include the resonance factor, firing angle alpha of the forward facing thyristor as measured from the positive reaching a zero crossing of the capacitor voltage is reached, which is constrained in the range of minimum alpha that should be less than or equals to alpha less than or equals to maximum alpha case. So this constraints provides a continuous Vernier control for TCSC module reactance operation. So maximum TCS reactance is permissible with only alpha equals to alpha minimum with typically 2.5 to 3 times of the capacitor reactance. That should be happens at fundamental frequency. So usually here loop current is increasing as alpha and it is decreased to up to 180 degrees to alpha minimum. So 180 degrees to alpha minimum it is going to reach. So another variant is the inductive Vernier mode. So in which TCSC can be operated by having a high level of thyristor conduction case. So in this mode what happens means direction of circulating current is reversed and the controllable presents a net inductive impedance as C is in parallel with L and the flow of current will take place inside this region with the connection of anti-parallel to thyristors T1 and T2. The same case which is assumed to be extended with the current as I in the reverse direction means the C existing with the anti-parallel of two thyristors and inductors existence will be there in the circuit. So based on the three modes of thyristor valve operation, two variants of the TCSC going to be emerges. So that is a thyristor switched series capacitor TSSC, which permits a discrete control of the capacitive reactance. So thyristor controlled series capacitor, which offers continuous control of capacitive or inductive reactance. So TCSC, however, is more commonly employed in this case. So analysis of the TCSC here. So here analysis of the TCSC operation in the vernier control mode is performed based on the simplified TCSC circuit. This gives the brief information regarding simplified mode. So transmission line current is assumed to be independent input variable and is modeled as an external current source IS of T. IS of T. So it is further assumed that line current is sinusoidal in nature as it is derived from the actual measures that will demonstrate that very few harmonics are exist in the line current case. So however, that analysis is presented in the following context. It may be suitable to the extent when the line current deviates from purely sinusoidal in nature. This may happen usually. So coming to this, the existence of the voltage across the capacitor is Vc of t existing across that capacitor, then the switch command is derived here to make the inductor to release its energy from the coefficient of coupling case. So current through the fixed series capacitor as it is expressed as C into dVc by dt, which is as Is of t minus it of t with u phase. So switching variable is u equals to 1. When thyristor valves are conducting in nature, that is when the switch is closed. So on the other hand, u is 0 means when the thyristors are blocked, then switch is going to be opened in manner. So thyristor valve current, that is it of t, is then described by L into dit of t by dt is equals to voltage across capacitor into U. Here the line current Is of t will be represented by Is of t equals to Im cos omega t. So whatever the expression shown here can be solved with the knowledge of the instance of switching. So with that instance of switching, in equidistant firing pulse control schemes for balanced TCSC operation, thyristors are switched on twice in each cycle of line current. So at this instance, T1 and T3 are obtained as T1 equals to minus beta by omega, T3 equals to pi minus beta by omega are the two expressions relating to this case. So beta is the angle of the advance here before the forward voltage becomes 0, or we may treat beta as pi minus alpha. This should be ranging from 0 less than or equals to beta less than or equals to beta max. So firing angle alpha is generated using a reference signal that can be in phase with the capacitor voltage. So thyristor is switched on off at the instance T2 and T4. They may be defined as T2 equals to T1 plus sigma by omega and T4 equals to T3 plus sigma by omega, where sigma is the conduction angle which is assumed to be same in both the positive and the negative cycles of the conduction case, and also there will be sigma equals to 2 beta case. So solving for the TCSC expressions which may result in steady state conduction of thyristor currents as it equals to k square by k square minus 2 cos omega t minus cos beta by cos k beta cos omega r t is the expression that is solving from the TCSC expressions which are resulting from the steady state thyristor currents usually. So here omega r is treated 1 by root LC, where k is omega r by omega here, that is v into 1 by omega l into 1 by omega c, where v into xc by xl is considered, where xc is the capacitive reactance, xc is the capacitive reactance, XL is the inductive reactance. Inductive reactance. So, nominal reactance of the system is usually considered. So, steady state capacitor voltage at the instant of omega t is minus beta considered as Vc1, that is Im into Xc by k square minus 1 into sin beta minus k cos beta into tan k beta is considered. So at omega t equals to beta, it equals to 0 and the capacitor voltage is reached, then Vc of omega t equals to beta, which is equivalent to Vc2 and it is equivalent to minus Vc1. So capacitor voltage is finally obtained as Vc of t equals to Im into Xc by k square minus 1. So that is multiplied with minus sin omega t plus k into cos beta by cos k beta sin omega t. Here Vc coefficient must be added with Vc2, Vc of t as Vc2 plus Im of Xc as sin omega t minus sin beta is considered. So this is the condition which we existing. So because of the non-sinusoidal capacitor voltage Vc, it has a odd symmetry about the axis, that is omega t equals to 0. So fundamental component with the Vcf is obtained as 4 by pi integral of 0 to V of t sin omega t d omega t is considered. So XTCSC reactance, that is reactance of TCSC is about Vcf by Im is going to consider. So here reactance coefficient as V by I, that is Vcf by Im as Xc minus Xc square by Xc minus XL, that will be with 2 beta plus sin 2 beta by pi. So this will be added to the 4Xc square as Xc minus XL is considered with cos square beta by k square minus 1 coefficient with k tan k beta minus tan beta by pi. These coefficients are treated for reactance of the TCSC case. So here when the modes of operation existing, here the net reactance versus alpha angle can be drawn as one of the characteristics. This is inductive in nature, this will be capacitive in nature. So the graph region containing as inductive nature, which covers about all the parts of this graph, and capacitive region boundaries are denoted with these conditions. So capacitive mode for alpha as 150 degrees treated usually 150 degrees. So that is about in kV to the total voltage that will be drawn as one of the curve starting from negative coefficients to the positive coefficients of the values. They may vary like 4, 4.1, like that we can expect to write some more values for the TCSC voltage case. When it is the line current case, then the line current drawn becomes like this. This is the line current drawn. Similarly, capacitor current is drawn as one of the peaks. This is called capacitor currents. So the peaks may be expected in the capacitor currents, which may be containing any ripples, means we can suppose to introduce one of the filter circuits. They will ready to occupy and nullify the portion occupied by that waveforms. So this wave represents the current case, that is I about TCR. So the current that is existing in kiloamps range will follows the graph here, and this extent may follows to the suitable range, and the voltage valve case is going to be extended like this. This is called valve voltage, which may rises to the boundary levels that goes on increasing with respect to the time factors case. When indicative mode is introduced at an angle of alpha is equals to 130 degrees case, then TCSC voltage will follows with rise and decremental case of the wave nature. This may leads to the TCS voltage, and the line current is treated here. This is called line current, and the capacitor current may goes up and down. This is called capacitor current. So these are the voltage and currents which follows in kilovolts, kiloamps range means, which resembles for inductive mode of operation. They are existing at an angle of alpha 130 degrees case. And this wave will represent one of the TCR current means the peaks are generated at a maximal case and they maintain the consistency of the wave to the suitable extent. Here this is valve voltage. So valve voltage becomes abrupt change in voltage. This is called abrupt change in voltage with respect to the valve voltage case. So another basic operation about various schemes of GCSC, TSSC and TCSC are introduced here. So for the functions of the operating or internal control of the variable impedance, type compensator is ready to provide appropriate gate drive, then thyristor valve is ready to produce compensating voltage or impedance which are defined by one of the reference case. So internal control is ready to operate the whole power circuit of the series compensator and which may enables to function in a self-sustained manner as a variable reactive impedance case. So power circuit of the series compensator together with the internal controls can be viewed as block box. So impedance amplifier, the output of which can be varied from the input with a lower power reference signal. So reference to the internal control is provided by external or system voltage whose function is to operate the controllable reactive impedance. So it is to accomplish specified compensation objectives of the suitable transmission lines. So in the point of external control receives a line impedance. So current, power or angle reference ends are going to be treated within measured system variables. So which derives the operating reference for the internal control. So structurally the internal controls for three variables impedance type compensators are GCSC, TCSC and TSSC. That should be similar in nature. So here it may shows that the functionality is simply to define the conduction and or the blocking intervals of the valve in relation to the fundamental power frequency component of the line current. So this requires the execution of three basic functions. So that is about synchronization to the line current, turn on or turn off of delay angle computation and gate firing signal generations. So whichever the functions obviously can be implemented by different circuit approaches with differentiating advantages and disadvantages of the circuit. So in the possible internal control schemes which are functionally discussed as one of the GCSC methods and other two for the TCSC power circuit arrangements. So these are cumulatively compounded methods. So either of the TCSC schemes could be adopted for the TSSC if subsynchronous resonance would be application concern. That means internal control scheme for the GCSC is going to be considered. This is arranged with the reference voltage signal. So this is connecting to voltage to turn off the delay angle converter as VCA of gamma equals to gamma. So synchronous timing PLL circuit is designed here. With this connected to the gate driven circuit, this is going to be connecting to the capacitor voltage sensing and processing circuit which is connected to the VC case. And these blocks are connecting to one of the anti-parallel combinations of the thyristors. They are connected as one of the capacitors across the voltage. So the wave which is taken as the reference wave here, and with respect to that the peak pulses generated will be following to the respective wave nature. So as it is going to be turned to the nearest case with respect to gamma, this may be treated as gamma 1, gamma 2, gamma 3, gamma 4 respectively. So f of gamma are the functions of the wave which may disables here. So that may be as one of the function k into 1 minus 2 pi gamma minus 1 by pi to gamma. So this is about the off period, and Vc will be the capacitor voltage, and with this Vc of gamma will be following this case. And on-state power stages are derived here with respect to peaks generated at each instant of the time. That is called as valve turn-on time. So here the first function is synchronous timing, which is provided by phased lock loop circuit that runs in synchronism with the line current case. So second function is the reactive voltage or impedance to turn off delay angle conversion, that is according to the relationship respective. So third function is here determination of the instant of valve that may be turned on when the capacitor voltage becomes 0. That is, this may be also including the maintenance of minimum on time at voltage 0 crossings. This is to ensure immunity to subsynchronous resonance case. So here the fourth function is the generation of suitable turn off and turn on pump. This is for the GTO valve case, gate turn off valve case. This will be suitable. So here the basic GCSC power circuit plus internal control action can be considered as one of the controllable series capacitor which is responding to the transmission line current, which will produce as with a given frequency band and specified rating case. So the compensating impedance are defined by the reference input case. So dynamic performance of the GCSC is similar in nature to the TCR case. Both are having the maximum transport lag of 1/2 a cycle. So internal control scheme is existing here for the TCSC. So main consideration here is to the structure of internal control operating the power circuit of the TCS. This is to ensure immunity to subsynchronous resonance. So present approaches here following the two basic control philosophies. So here one is to operate the basic phased lock loop PLL. This is from the fundamental component of the line current, and with this the reference signal generated will be Vc with the Vc reference case. Here error amplifier circuit is designed with the PI controller case. PI controller case. This is connecting to the block of synchronous timing, which is connected to the PLL block. So this block is connecting current to delay angle converter case. So filters and phased correction circuits are supposed to be coupled to the gate pulse generation cases, which all together meeting to TCSC case as they connected in series and parallel combinations of the devices. So in order to achieve all these aspects, it is necessary to provide substantial filtering to remove the super and partial case of the subsynchronous components. This is from the line current, and at the same time we will maintain the correct phase relationships for proper synchronization case. So a possible internal control structure is supposed to be derived to make the circuit operation free. So in this arrangement, the conventional techniques for converting the demanded TCR current into the corresponding delay angle is considered. So which is measured from the peak with a fixed value of 90 degrees phase shift from the 0 crossings. This should be reaching to the fundamental line currents whichever used. So reference for the demanded TCR current is usually provided by regulation loop of the external control circuit. So here which compares the actual capacity impedance or compensating voltage. This is to the reference given for the desired system of operation. So second approach also employs a PLL logic scheme. So synchronized to the line current for the generation of basic timing circuits with reference to the main case. So however, all these approach methods reaches to the actual 0 crossings of the capacitor voltage, which are estimated from the prevailing capacitor voltage and line currents by an angle correction circuit arrangement. So delay angle is then here determined from the desired angle, and then it is estimated to correction angle. This is so as to make the TCR conduction symmetrical in nature with respect to the expected 0 crossing levels. So desired delay angle is in this scheme can be adjusted by a closed loop controlled phase shift. So this is as the basic time reference provided by the PLL circuit case. So delay angle of the TCR and thus compensating capacitive voltage as in the previous case is controlled overall by regulation loop of the external control circuit. This is in order to meet the system operating requirements. So this regulation loop is relatively slow with a bandwidth, just this is sufficient to meet the compensation requirements as power flow adjustment is making power oscillation dampings and arms. So that is thus it is from the standard point of view, angle correction circuit which is by comparison is very fast. That means correction takes place in each half cycle. So output of the phase shifter is almost as steady state reference. So although the control circuit performance are usually heavily dependent on the actual implementation, so second approach is theoretically more likely to provide faster response for the applications requiring such response case. So error amplifier introduced here with respect to the PI controller by exciting the circuit with one of the capacitive voltage. This reference voltage at summing point will generate the signal and connecting to the PI controller. Here it will smoothens the error signal and controllable phase shifter it is connecting as advance or retard stage. So synchronous timing circuit is one of the circuit coupling to one of the current block and VC block as angle correction circuits. So this may be connected to the gate pulse generator. The whole of the combination will be treated as a TCR gating signal control. So this TCSC combination connecting in parallel to the capacitor case means inductor will act to the responses generated by the circuit. So this functional internal control scheme is designed based on the TCSC on the prediction of the capacitor voltage zero crossing levels. So with this we can achieve suitable efficiency of the system. So these are some of the references whichever I have considered, and this gives the information about all the controllers which are derived for the power system network suitable. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.